Hello, everyone, and welcome to Ask the Experts. I'm Tim Messagy, and I'm joined by my memory expert, John Eble, who is Vice President of Product Marketing for Memory Interface Chips here at Rambus. Welcome, John.
Thank you, Tim, and hello to everyone out there. It's a real privilege to be able to talk with you today.
Thanks, John. Why don't we kick off with a question? Um, for DDR5 for servers, you've got this advanced chipset that allows you to get more bandwidth and more capacity while maintaining the same power envelope that we saw for modules for DDR4. Are you seeing a similar development on the client side?
Yes, Tim, we are seeing the need for advanced chipsets for client DIMMs and client systems as well. While server systems do have specific requirements, such as RAS and very high capacity support, a number of the things between the two systems are similar. The DDR5 interface operates with the same protocol, the same speeds, and therefore a lot of the challenges are common between the two. A lot of these challenges stem from the precise timing that's required. The memory subsystem is a synchronous system. So the CPU launches a clock, which is the timing reference. It expects all DRAM accesses to be deterministic in latency. That means when at time zero, it launches a command, it expects X clock cycles later that it will receive that data and that it will sample it at that time. So the real challenge in these systems, both server and client, is to make sure that the accumulated timing uncertainty or jitter in this round trip is low enough so that they're margin at these very high speeds. So in summary, as we continue to go to higher and higher frequencies, we do see the need for a more robust chipset for client DIMMs.
Thank you, John. So Rambus has just announced a client clock driver. Can you tell us about the role of that particular chip and what are the use cases?
The clock driver is solving really a jitter and timing uncertainty problem. So let's talk a little bit about what happens today in a client system. The CPU sends out that reference clock that I mentioned, and that's generated on the CPU, which is a very large chip. It's power hungry. There's noise there. That clock then needs to escape through a large pin field onto the motherboard, goes across the motherboard up through a DIMM socket, and then it fans out to multiple DRAM devices on the DIMM. And a lot of these paths that I just mentioned are frequency limited. So as we go up in speed, this particular path introduces more and more jitter. So what the clock driver does is it's integrated very near the memory on a UDIMM or an SODIMM, or maybe even on the motherboard in a die-down type of application. And it receives the clock on the module. So it can be positioned close to the pins. It receives the clock. And then it redrives this clock. It redrives multiple copies. And not only does it restore the amplitude of the clock, but it also cleans up and retimes the signal so that it's relatively noise-free from a timing perspective. So the real value here is that it reduces jitter in the synchronous system and allows us to have sufficient margin to close the timing budget as we scale up to frequencies of 6400 and beyond. In terms of use cases, these are on client modules or on the motherboard, if that's where the DRAM is. To denote the presence of this clock driver, you'll start to see modules that are called CUDIMM and CSODIMM. One secondary value I'll mention about the clock driver is that today the CPU will send out as many as 4 different clocks to the UDIMM or the SODIMM. And with this type of architecture with the clock driver on the module, There are opportunities to reduce power on the CPU by it only having to send a single clock pair that the clock driver then multiplies up, and potentially save pins on the CPU package itself.
Okay, so John, when UDIMMs and SODIMMs launched for DDR5 at 4800, those didn't have client clock drivers. What happens at 6400 and above that we now need that component in the chipset?
As we go up in frequency, the cycle time reduces, the bit time reduces, and the jitter needs to scale down proportionally. So, this jitter reduction gets harder and harder as we go up in frequency. And at some point, that may break and we need to do something differently. The other thing working against us is that at higher frequencies, a lot of the interference mechanisms that reduce signal integrity, such as reflections due to impedance discontinuities, crosstalk, and the physical effects that cause loss in the signal and distort it, all those get much worse at higher frequencies. So it's right about at 6400 where we start to see those components getting big enough and our ability to drive down the jitter low enough to where it's hard to close the timing budget. And what the industry decided to do to solve this problem was to introduce an active component in that path to help manage the overall jitter and be able to close the timing budget in order to have a robust system.
John, in the data center, DDR5's been this critical enabler for AI, both training and inference. But in client, what applications are driving this need to keep pushing performance up?
We're definitely seeing AI and applications that utilize AI drive a real renaissance in the PC. I think we'd all love to have our own personal assistant on our screen. For those old enough, think about a Clippy on steroids. So platforms launching later this year and ramping in 2025 will be marketed as AI PCs, those with dedicated hardware optimized for inferencing. AI inferencing requires high memory capacity and bandwidth to be able to give real-time results from a large model that's contained on your PC. These systems will use 6400 megatransfer per second DDR5 memory on modules that I just talked about, the CU DIMM and CSO DIMM. And those modules are part of the overall architecture to tackle these computational and memory-intensive workloads. The rapid development of AI models and new AI applications and the use cases that they enable will continue to drive client memory requirements. Our recent announcement of the clock driver supports these PCs and modules running at 6400, and this product extends up to the next speed bin on the roadmap of 7200. So we'll be following on and being able to support that next generation as well.
Thank you, John. My final question is this. It's the why Rambus. What does Rambus bring to chips for the client space?
Good question, Tim. Rambus has been an innovator in the memory space and developing memory subsystems for over 30 years. We've had a lot of ingredient innovations along the way that have gone into these subsystems, and these have been necessary to support both servers and feeding multi-core CPUs, as well as for client CPUs that are now bringing in more of this acceleration feature and just lots of computation. And the demand will continue to grow, and we will continue to innovate solutions. And in order to hit these speeds, as I've mentioned, you really need to manage both the power integrity and the signal integrity. And that's where Rambus has a lot of expertise. It's really our core competency. It's something we've been doing for quite a while.
Exactly.
In addition to that, Rambus more recently, over the last 10 years, has really become a first-class semiconductor product company where we have lots of high volume experience in house. We have strong partners both in the supply chain, in the memory industry, and the end customer. So we really have a strong track record there. So, moving into the client space is a very natural move for
Hmm.
us from servers. We're still in memory. We did do an announcement of SPD Hub sometime back, which is really our first foray in the client. The clock driver will be a really big part of this. And, we will have additional chips to announce in the future for both server and client.
Excellent, John. Well, we'll look forward to that. So I want to thank you for being on Ask the Experts and for everybody who joined us today. Thank you for your time being here on Ask the Experts, and we'll see you again real soon.
Yep. Thank you, everyone.